We present a decentralized algorithm to achieve segregation into an arbitrary number of groups with swarms of autonomous robots. The distinguishing feature of our approach is in the minimalistic assumptions on which it is based. The robots are equipped with a single ternary sensor, and the controller directly maps the sensor readings to the wheel speeds with a simple if-else statement. The best wheel speeds were found with a grid search. Finally, we provide conditions for guaranteed convergence and study the scalability and non-ideal aspects of our method. The theoretical sensor used in our study can detect robots in a straight line infinitely far in front of the robot. The sensor value 0 indicates no robot, the value of 1 indicates a kin robot, and 2 indicates a non-kin robot. Note that the robots need not distinguish between different classes of non-kin. Through grid search, we discovered that these parameters achieved the lowest cost. To demonstrate how this controller works, imagine at time 0 the robot sees nothing. It will then execute the wheel speeds -1 and -2/3, which cause the robot to arc in a clockwise direction. Then, at some later point, it may see a kin robot, which causes the robot to arc counterclockwise. It then no longer sees the kin, and will then arc back clockwise towards the robot. In this way, the kin robots zigzag towards each other. Here we show some examples of how our controller runs in simulation. Kin robots tend to form rings. The rings are robust, and if non-kin robots disrupt the pattern, it will reform. We consider how the number of robots, beam length, and beam angle affect the segregation performance. To study scalability, we first observe how the cost changes when the number of robots per class is increased from 4 to 100, with a fixed 100 total robots. We find that our controller performs very well, even at 25 classes with just 4 robots each. The kin robots quickly pack together, which reduces the number of occlusions and increases free space. Next, we fixed the number of robots per class to 10, and increased the number of groups from 1 to 20. This implies that the total number of robots in the environment changes from 10 to 200. The average cost increases with the number of groups, which we attribute to the increased number of occlusions and reduction in free space from the added robots. Please see the link to the YouTube playlist of videos in our paper. Thank you.